we continue our discussion on discrete random variables. Again, recall, a discrete random variable is a random variable that can take on at most a countable number of possible values. We refer to it as a discrete random variable. We are now going to focus only on discrete random variables. Again, when we look at discrete random variables, let I denote a random variable with the uppercase x, y, z, x1, x2, x3, y1, y2, y3 and so forth, or z1, z2, z3. This is typically we represent a random variable through uppercase alphabets, capital X, Y, Z. So now let X be a random variable. Let it take a finite number of values. So what do I mean by it takes a finite number of values? It takes n possible values. Let me represent that by x1, x2, xn. For example, if x takes the values 1, 2, 3, my x1 would have been 1, x2 would have been 2, x3 would have been 3. If x takes the value 1, 2, 3, 4, as in the case of the number of floors, this was the number of bedrooms, this is the floor, then x1 is 1, x2 is 2, x3 is taking the value 3 and x4 is 4. So, in general, I can talk of this random variable x taking values x1, x2, xn. That's what I mean by x is taking n finite values x1, x2, xn. Once I know x1, x takes these values, we define the probability mass function. How do I define it? This is a function for all the values. What are the values x is taking? X is taking values x1, x2, xn. So, associated with every value x takes, I know there's a probability associated with it. So, I have what is the probability of x taking the value x1. I know what is the probability of x taking the value x2 and x taking the value xn. This function, the probability of x equal to xi for each of these values, this function is referred to as the probability mass function of the random variable. A nice way to represent it is in tabular form. So, x takes the values x1, x2, x3 up to xn. The probabilities is with probability x equal to x1 is px1, px2, px3 up to pxn. So, let's look at a very simple example. Before the example, so here we assume that this x takes finite number of values. So, x takes x1, x2, xn possible values, but I could also have the case that x assumes value x1, x2, x3 countable but infinite. Again, associated with each of these xi's, I'll have a p of x1, I'll have a p of x2, I'll have a p of x3, so forth. So, whenever I talk about a discrete random variable, I could either have countably finite or countably infinite number of values. But nevertheless, whatever it is, there are two key properties of the probability mass function. I repeat, there are two key properties of the probability mass function. They are namely probability of xi is greater or equal to 0. In other words, probability x equal to xi is always non-negative. And the second property is that some probability of x equal to 0 for all values of x. So, if I represent it in tabular form, I have P of xi is greater or equal to 0 for all I, and the next property is, since x, I know that every point in my sample space, for example, if my sample space in the apartment complex was 1 to up to 12, every point was mapped to a random variable. We also know from the axioms of probability, the probability of S is equal to 1. Since every point is mapped onto a random variable, it makes sense for us to say that the summation over all possible values x can take, the summation of the probabilities should add up to 1. So, the two key properties are probability of xi is non-negative and the summation of over all possible values of x should be equal to 1. Now, if x takes only finitely many values with probability p of x1, p of xn, then I know summation I going from 1 to n, p of xi should be equal to 1. Some books refer p of xi with just pi, but we need to understand that whenever you see a pi, this could be probability x takes the value xi or probability x takes a value I. You need to understand how the probability mass function is defined. But nevertheless, however you are defining the probability mass function, the probability of x taking a particular value is always non-negative, and the sum of probabilities over all possible values should be equal to 1. These are the key properties of the probability mass function. Now, let's look at an example. Suppose x is a random variable that takes 3 values. So, again I have a random variable which takes only 3 values. It is finite, 0, 1, 2. And what is the probability? Probability x equal to 0 is 1 by 4, x equal to 1 is half, and x equal to 2 is 1 by 4. Tabularly, I can represent it as x takes the value 0, 1 and 2. So, my x1, x2, x3, x1 takes 0, 1 and 2 with probability x equal to x1, which is a 0, is 1 by 4, x equal to x2, which is probability x equal to 1 is 1 by 2, and x equal to x3, which is x equal to 2 is 1 by 4. So, what is the first property I need to see? Probability of xi is greater or equal to 0. I know probability of x1 is 1 by 4. This is greater than 0. Probability of x2 is 1 by 2, which is greater than 0. Probability of x3 is 1 by 4, which is also greater than 0. The second property is summation. I going from 1 to n, p of xi should be equal to 1. In other words, I need to verify whether p of x1 plus p of x2 plus p of x3 equal to 1. This is what I need to verify. I can see that p of x1 is 1 by 4, p of x2 is 1 by 2, p of x3 is 1 by 4. I can verify that this is equal to 1. Hence, what we have here is a probability mass function of the random variable. Let's look at certain more examples to understand the properties of the probability mass function. Now, suppose I have x is a random variable that takes values 1, 2, 3, 4, 5. So, I have this is my x1, x2, x3, x4, x5. Again, it takes finite number of values with the given probabilities. So, is this a probability mass function? So, the first condition is I need to check probability of xi is greater or equal to 0. Yes, for this, done. This is greater or equal to 0. This greater or equal to 0. This greater or equal to 0. This is also greater or equal to 0. The next condition, so the first condition is satisfied. Now, the second condition is I need to check whether probability of I going from 1 to 5 is equal to 1. So, I have a 0.4 plus 0.1 which is a 0.5. 0.5 plus 0.2 which is a 0.7, 0.7 plus 0.1 which is a 0.8, 0.8 plus 0.3 which is 1.1. So, I get the summation xi is not equal to 1. Hence, this does not satisfy the probability properties of a probability mass function. Hence, the first table is not a probability mass function. Now, let us look at the second example. Again, x is taking the value 1, 2, 3, 4 and 5. So, the first property, probability of xi is greater or equal to 0. Here it is yes, yes, yes. This is a no, this is a yes. So, you can see that probability of x4 is not greater or equal to 0. However, if you notice summation p of xi, I going from 1 to 5 which is equal to 0.2 plus 0.3 plus 0.4 minus 0.1 plus 0.2, you can see that this is 0.9 which is equal to 1. So, I have a situation here where the function satisfies the second property but not the first property. Hence, because of this, it is not a probability mass function. So, here it violates summation p of xi equal to 1 over all values of I. Here it violates the p of xi is greater or equal to 0. Now, let us look at a third example. In this example, again x takes the value x1, x2, x3, x4 and x5 with these probabilities. Again, let me check the first condition. Greater or equal to 0, greater or equal to 0, greater than 0, greater or equal to 0, greater or equal to 0. First condition, it's satisfied. First condition is p of xi is greater or equal to 0, satisfied. Now, let's check the second condition, which is summation p of xi, I going from 1 to 5, 0.3 plus 0.1, 0.4, 0.4 plus 0.2, 0.6, 0.6 plus 0.4, 1, 1 plus 0.0, 1 plus 0 is 1. Yes, it is equal to 1. So, both the conditions are satisfied. Hence, this is a probability mass function. So, the first thing which you need to understand is, given a random variable, again I specify we are looking only at discrete random variables. So, given a random variable x that takes the values x1, x2 up to xn. For the first case, I considered countably finite number of values. If I am talking about a probability mass function, I need the two properties. And what are the two properties we are looking at when we are talking about a probability mass function? The first is probability of xi is greater or equal to 0. And the second is summation probability of xi over all possible values of x should be equal to 1. Now, let us look at another example where x does not take finite number of values. It takes countable number of values but not finite. So, let us look at this example. So, what are the values this random variable is taking? X is taking the value 0, 1, 2, 3. It keeps taking these values. Let me write probability x equal to xi, probability of x0 or x1, x2, probability of x3, probability of x4. So, this is my x1, x2, x3, x4. So, x is taking these values. Okay, I am not having finite number of values. So, now what is it? The probability of x equal to I is given by C lambda to the power of I by I factorial. Okay. Now, lambda is positive, I is greater or equal to 0 because I takes the value 0, 1, 2, all of it. So, I want to know for what value of C will this be a probability mass function. Again, what are the values X is taking? X takes the value 0, 1, 2, 3, so forth. Probability X equal to 0 would be C times lambda to the power of 0 by 0 factorial. This would be C times lambda to the power of 1 by 1 factorial. This would be C times lambda to the power of 2 by 2 factorial, and so forth. So, what value of C would make this a probability mass function? So, the first thing is I know lambda is positive and I is positive. So, C has to be greater or equal to 0, because again what are the conditions? The conditions of P of xi should be greater or equal to 0, and summation I going from 1 to infinity P of xi should be equal to 1. For the first condition, I need C to be non-negative because everything else is going to be non-negative. For the second condition, I need to check C into lambda to the power of I by I factorial, I going from 0 to infinity should be equal to 1. So, what value of C would give this? This is what we need to check, because for this to be a probability mass function, I need this condition to be satisfied. So, the question is, what is the value of C for which this is a probability mass function? So, this is I goes from 0 to infinity. So, I will have again, I am sorry about this, this is again I goes from 0 to infinity. Okay. So, I know it's again 0 to infinity here. So, I goes from 0 to infinity C lambda to the power of I by, because x takes the value 0, 1, 2, I need to look at I goes from 0 to infinity. Now, we all know the following, that e to the power of x is, so we all know the following, that e to the power of x is summation I going from 0 to infinity x to the power of I by I factorial. Hence, I have summation I going from 0 to infinity C to the power of lambda I by I factorial is C e to the power of lambda, because this would be e to the power of lambda. So, now I have from here C into e. So, this term is going to be e to the power of lambda. That is what this tells us, that summation xi by I factorial is e to the power of x. So, this term would be e to the power of lambda. So, I get C into e to the power of lambda is equal to 1, which would give me C equal to 1 by e to the power of lambda or e to the power of minus lambda. Hence, I get my P of I is e to the power of minus lambda, lambda to the power of I by I factorial. Okay, so I can get my C to be e to the power minus lambda, which is going to give me the solution that P of I is e to the power of minus lambda, lambda to the power of I by I factorial. Now, let us go back to the examples which we have discussed earlier. So, we looked at the first example we looked at was rolling a dice twice. We know that the sample space has 36 outcomes, and I have listed down the 36 outcomes here, which are 1, 1 to 6, 6. Now, let us define the random variable, which is defined as the sum of outcomes. Again, we have seen this in the earlier lecture, that every outcome is mapped to a particular value. So you can see that 1, 1 is mapped to 2, 1, 2 is mapped to 3, 1, 3 is mapped to 4, 6, 6 is mapped to 12, 6, 5 is mapped to 11, the sum of outcomes. So I can see that this random variable x takes the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. These are the values this random variable take. X takes the value 2, 1, 1 is the outcome which maps to it. X takes the value 3, 1, 2 and 2, 1 are the outcomes that give the value 3. 4, 1, 3, 2, 2 and 3, 1. So each one of them you can see is mapped. 12 is from the outcome 6, 6. Now again associated with each one of these values, probability x equal to I. So associated, what is the probability x equal to 2? I know only one outcome gives this value. So it is 1 by 36. 1, 2 and 2, 1 here. So this is 2 by 36. X equal to 4 comes from 1, 3, 2, 2 and 3, 1. 3 by 36. X equal to 5. I have 1, 4. I have 2, 3. I have 3, 2. I have 4, 1. So it is 4 by 36. This would, you can check as 5 by 36. X equal to 7 is 1, 6, 2, 5, 3, 4, 4, 3, 5, 1 and 5, 2 and 6, 1, which is 6 by 36. Okay. Similarly, this would again 8. I know 8 would come from a 6, 2, 5, 3, 4, 4, 3, 5. Okay. And a 2, 6. So again, this is 5 by 36. You can verify for all other values. This is going to be my probability mass function. So I know x takes the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 with the probability this one. Now, is this a probability mass function? Again, what are the properties of the probability mass function? This should be greater or equal to 0. I can see each one of them is greater or equal to 0. The second thing we need to verify is the sum of the all probabilities I going from all xi. So, this is x1, x2, x3, x4, x5, x6, x7, x8, x9, x10 and x11. I going from 1 to 11 should be equal to 1, 3, 3 plus 3, 6, 10, 15, 21, 26. 26 plus, again you can see plus 10 is 36. So you can see that this is 36 over 36, which is equal to 1. And I can see that this indeed is a probability mass function. Now, let's go to the second random variable which we defined. Again, we defined the second variable which takes the lesser of the values of the outcomes. So, again, I have y. Y takes the value 1 for these outcomes. So, for all these outcomes, y takes the values 1. Y takes the value 2 for these outcomes. It takes the value 3 for these outcomes. It takes the value 4 for these outcomes. It takes the value 5 for these outcomes. And it takes the value 6 for this outcome. So, this is 1 by 36. 5, 1, 2, 3. So, this is a 3 by 36. 4 would be 5 by 36. For 3, it was 7 by 36. 2 it was 9 by 36, and 1 11 out of these outcomes, probability y equal to I. So, I know y takes these values with the respective probabilities. Again, is this a probability mass function? Let's verify. I know all of them are greater than or equal to 0. So, the first property is satisfied. The second property, 11 plus 9, 20, 20 plus 7, 27, 32, 35, 36. It is actually 36 by 36, which equal to 1. So, I have both the properties are satisfied, and hence this also defines a probability mass function. Now, let's look at the next example of tossing a coin 3 times. Now, when I toss a coin 3 times, again this is my sample space. Again, we defined x to be the random variable that counts the number of heads in the toss. Again, this outcome, it is 3. Here I have 2, here I have 2, here I have 1. Again, 2, I have 1 head, and no head. So, x takes the value 0, 1, 2, and 3. With what probabilities? The probability with x takes no head, it corresponds to this outcome, it is 1 by 8. 3 heads corresponds to this outcome, which is again 1 by 8. 1 head, it corresponds to this, and this. So, it is 3 by 8. 2 corresponds to this, and this outcome, which is again 3 by 8. Now, is this a probability mass function? All of them are greater or equal to 0, and the sum of the probabilities, which is equal to 1 plus 3 plus 3 plus 1, is 8 by 8, which is equal to 1. So, hence it is indeed a probability mass function. So, the next thing which we can look at is the random variable which counts the toss in which head appears first. Again, here head appears first in the first toss. Again, here it appears in the first toss. Here it again appears first in the first toss. Here it appears in the first toss. Here it appears in the second toss. This is again second toss. This is third toss. And this is the nil toss. Remember, we defined it as nil, we did not define it as 0. So, the value y takes are again 1, 2, 3 and nil. And the probability with y takes those values, it takes the values 1, 4 out of 8, 2, 2 out of 8, 3, 1 out of 8 and nil, 1 out of 8. All of them are greater or equal to 0. The second property, I need to check whether they add up to 1, which is 8 by 8, which is equal to 1. And I can see that this indeed is again a probability mass function. So, by this time, what you have to understand is what is a probability mass function. Again, remember, we are talking only about a discrete random variable. So, what we are looking at is we have defined a discrete random variable which can take finite number of values, or it can take countably infinite number of values with probability x equal to xi, which is p of x1, p of x2, p of xn. Again, same thing when it takes countably infinite number of values, p of x1, p of x2. I say it's a probability mass function if each of the p of xi is greater or equal to 0 and summation over all possible values of xi should be equal to 1, then it is a probability mass function. So, the next is, can I graph this probability mass function? So, that is what we are going to look next.